Yeah.
SIG.
Yeah. So, hello everyone. Welcome to Enterprise Agile Meetup. Our purpose is to discuss Agile generally for large companies and organizations and how to adopt and change companies and organizations. And we've been doing this for, I don't know, like 7, 8 years now. Holy crap. It's been a while. And we've had a lot of great visitors and guests to come in and talk. No exception today or tonight. We have great visitors and guests to talk about something that's probably on people's minds, like, how do we use these tools, individuals' interactions over tools and processes. And so I'm going to turn it over to Ron McPeak and have him introduce our guest. So Ron, go ahead.
So I think, Krishna, that we've known each other for 4 years.
Almost 4 years, yeah.
So something like that. And what I discovered, I'm not sure exactly what kicked off our meeting, but I was blogging or posting about metrics, and Krishna posted back about metrics, and we got into a conversation that made us realize that we were more aligned than I thought. Maybe not more aligned than you thought, Krishna, but we're actually pretty aligned. But that if I was going to pick somebody to share anything about metrics, I'd pick Krishna, and even over my co-author Mickey Mantle, who is a pretty metrics oriented guy and has been investigating metrics for decades as a VP of engineering and a CTO, and so whenever I see something about metrics that just sparks my attention and my interest, I'll try to engage both Mickey and Krishna to see what they think. And I ran across, it was probably 3 months ago, ran across a post that Krishna had done on Agile tools and Jira. Jira got called out specifically, but it wasn't specifically about Jira. But it was about Agile tools and whether they were helping or hurting, and it sparked a good conversation on one of the Agile forums. And I thought, and I popped it out to Jay and to Gopal and to Mary, my co-chairs here at the Enterprise Agile Global Community, and said, I think we want to see if we can get him to do this as a talk. And they all agreed, and so I invited Krishna to share. So with that, Krishna, I'll turn it over to you. I should note, Krishna is a consultant, and he parachutes into teams that and discovers ways in which metrics can help them be more effective. Is that a good description?
Yeah, absolutely. So
yeah. And in very interesting ways. So I'll turn it over to you, Krishna.
All right. Thanks, Ron. Thanks, everybody for having me. Yes. So yeah, today's talk should be interesting. As Ron said, we started out with a throwaway line on a LinkedIn post. It kind of turned into a conversation, and then when Ron said, okay, do you want to talk about it? And I was like, I don't think I have an hour's worth of stuff to talk about that particular post, but let's break it up into something a little bit bigger. And then I'll put some context into the why that post came about. And that's going to be the conversation today. So yeah, the tools, Agile tools is probably a little bit of a bait and switch when you get into the talk about it, but we will actually see how it fits in by the end of the talk. So, and I'm hoping that, you'll stop me with questions and stuff as we go along. This is hopefully an informal conversation. I have a bunch of slides. I don't have to go through all of them. It's a set of ideas that I've been working on for several years now as part of my practice. And I'll talk a little bit about that and how we use it, and then we'll get into the meat of metrics and so on and so forth. We can go as deep or as low level as the audience wants. And if you get tired of me speaking, stop me. So
And believe me,
that's
Krishna can go
I
deep.
can't talk. Okay, so let's get, if you don't mind, I will go off of video because I hate looking at myself on video. I'm looking at the screen. So, and I'll come back when we need to chat. All right, so let me talk a little bit about myself. I'm a software engineer, have been since the early 90s. My career track was pretty much your standard engineer career track. I did, engineering manager, architect, VP of engineering, CTO at mid-sized companies, small to mid-sized companies. The largest company I worked for was Oracle, and I lasted about 6 months there before I quit. So, so that's my background. And in 2011, I started my consultancy really as an independent FCTO practice. So I basically parachute into companies, help technology, process, architecture, grab bag of things that an interim CTO is supposed to help with, working with a few private equity firms. And then over the years, I realized that when I did this, I was always flying into companies blind, and I really wanted data to be able to sort of help both speed up my process of absorbing stuff, as well as being able to leave something behind that was more than just advice. And so it turned into something that I've been really sort of researching and doing some work on for at least since 2016. And as part of that process, I built a fairly sophisticated. I still write code. I still maintain a production system, and so I built this platform called Polaris, which is really you can think of it as kind of like a super duper version of many of the linear Bs and stuff tools out there, but it's actually a fairly sophisticated general purpose tool for value stream analysis, which is not, I use it only as part of my practice. So I don't sell it as a separate product, just because I just decided that there was more to that science of this thing than just sending a bunch of metrics. So one of my principles, I never do metrics. I go with goals and work backwards to the metrics I need to get them. And the platform helps me do that, right? And the program turned into something that was more repeatable in 2021. And so now I basically I run this as a software and advisory consultancy where I work with typically CTOs, sometimes CEOs of mid-sized software product companies. So my space is software product companies, not so much in the enterprise, but the problems are big enough that there's lots of overlap. So you'll see some of the product bias in the way I look at the world, but I'm really interested in connecting with more people who are in the enterprise space, because I do believe that this is the things we are working on are quite valuable even in the enterprise context. So the basic ideas are, when I started working on this, I was kind of winging it, building metrics and so on and so forth. But over time, I realized that there was a lot of good theory out there, queuing theory, operations research, and so on and so forth. But much of that was not really set up to work directly and well with software. So we had to sort of think through how does software differ from, let's say, assembly line manufacturing, or how does we process manufacturing? Because that's the bias that you see when you think about flow in most of the lean literature. While much of it is applicable, there are subtle differences in how software works. And so how do you actually take the good and adapt it to make it useful? And since this is somewhat, I would not call much of what I do truly mainstream. That's why I go along with it, because I want to make sure it gets used properly. And I'm learning as I go along. So even in the last couple of years, I've learned a tremendous amount about, how looking at actual data from the ground, understanding the theory, how it meets reality, how to morph it. It's been a process of kind of learning and research and consultancy and software building, which is really what I like to do. So it's a fit for what I want to do, right? So that's the background I'm coming from. So when we look at things like metrics, the way I look at this is it's not so much the metrics. You have to sort of figure out what problems you're trying to solve, and then work backwards to understand the theory and understand the measurement techniques for that, and then build the tools you need to build the right measurements at the right accuracy, right? So it's kind of a slow, painstaking process. I'll talk through that, talk about how that process works a little bit here if you guys are interested in whatever detail. But one of the things I find is that, you end up doing a lot of the same places that you would, if you were to say, okay, follow the Agile manifesto, right? The things that you have to do are well known. So we know what an Agile process is supposed to look like, the things you're supposed to focus on, but especially in the large, people just have a hard time making it work. Like, and part of the problem is that the systems, as they get larger, they get harder to reason about, right? And it's much harder to make change when you don't have data to back change up, right? And even in mid-sized software companies, companies with like 200 engineers, the invisibility of the process is a huge barrier, and bringing data to the table changes that equation very quickly. And I have concrete evidence of that. So that's me. That is the bias I bring into this. And where tools come in is typically when I go in and do an analysis and sort of look at the starting point. One of the biggest things that gets in the way that causes trouble with flow is the way people actually use tools and how they mediate the world through tools. Most of our modern tools are really sort of set up to inhibit or disrupt flow because they let people just do the absolute wrong thing, right? So I'll get to that point by the later part of the conversation, but just want to give you a little bit of background on how I'm going to get there. Does that sound cool? All right. All right, so today's talk, I'm going to start with product development flow. So what does this mean? If you're familiar with Don Reinertsen's famous book on product development flow, obviously that's the inspiration, but that's my starting point, basically adapting it to actual software work. And then how do we think about it? What are the basic principles of flow? How do we operationalize them on the ground? And I'll use one example called stability. And then how do the tools we use to manage the work get in the way? And what kind of anti-patterns do we get? What kind of patterns can we get to improve flow, right? Big high level overview, right? So when you say product development flow, I have a particular meaning when I talk about product development flow. It's basically you're looking at a system for software product development. So which basically looks like this conceptually. Typically a software product. When I say a product, what I mean is that this is something in the market, there's a product market fit. You already have an idea of what job you're helping a customer do. And so typically you can organize value streams in your system by the jobs to be done. And typically sub-jobs and sub-jobs and so on and so forth. Most product companies, in one way or the other, once you look deep enough, they tend to be organized by job, for customer-facing job, and they have value streams for them. They have multiple teams working on it. Typically, these individual product areas have different kinds of needs. You need new features, you need customer support, you need operations, and so on and so forth. These become sub-value streams in those jobs-based value streams. And then all of this is obviously in service of making and delivering changes to a code base, which is what makes the software, right? So if you didn't have, if you like, unlike any other product, the only way you actually add value to a product is changing code, right? In a sense, the unique way that we do it in software, right? So your world is basically a network of value streams based on products, jobs, and needs, relationships between teams, the code bases that they work on, and the work of getting changes in the code to a customer environment. So this is the lens I look at the world from. Obviously, this is not all software development, but it's good to have a grounding point to say, okay, what do we mean by the system? So the goal is, how do you understand the system better, right? And how do you sort of make the process of delivering value to your customer easier by understanding what are the impediments to making that happen as work flows through the system? Questions, thoughts, comments? All right. So my view, the worldview of software product development, what makes software unique? Whenever you talk about value streams, you'll typically see a diagram that looks something like this. Things going from stage A to stage B to stage 3, and so on and so forth. What makes software unique is that there are kind of two kinds of jobs in this process, right? One is kind of the cognitive work that we need to sort of collaborate with people, customers, to define and make changes to your code base. What are the needs? How do they translate into new requirements to change? How do you change the code? There's the actual sort of mechanics of engineering and product development. And then what I call assembly line work. So this is obviously a simplification, right? Once you have code that is changed and ready to be merged or integrated into a branch that can be shipped, in principle, this is assembly line work. In other words, obviously, we know that a lot of people do a whole bunch of manual work out here, but there is no real value to be added by doing that work manually. By the way, I don't mean QA here. For instance, QA can very well live here if it's a cognitive activity, right? But if you're running a set of manual test scripts 10 times a day, that's assembly line work, right? So essentially, we want to sort of have the distinction between the work that you can move into an assembly line, which is very much like lean. In other words, you can actually use a lot of the same principles to it. It's very repetitive. You can automate it and so on and so forth. But then the real part that is interesting is the cognitive work. So this is where flow becomes a very different beast, even though many of the underlying theorems in mathematics applies just as well, right? And the whole point of this is obviously to make this cycle of figuring out the delta in your needs and turning that into things that you can get delivered to the user as efficient as possible, right? So define, make, and ship incremental changes to a shared code base so that your product can help a user do a job better. That's what I call software development. Okay. Any questions, comments? Is that a reasonable definition? Right. Okay, so that's a basic. So now when we look at this system, right, I showed you a fairly complex system over here, right, a couple of slides back. When I look at a system, typically there's this whole debate about, can we even reason about these things, in any kind of sane way? Does mathematics apply? Is this one of those systems which is completely unknowable because it is a complex, adaptive, dynamic system? And so on. And I think there's certainly a lot of truth to it. And if you look at kind of the framing from Knefin, and Dave Snowden and others, it is all about the perception, right? What is your perception of your system, right? And the reality is, for most actual software systems out there, your perception is that it lacks constraint and it is chaotic, and you are reacting to things as they come along. I mean, that is certainly, if I look at any software company I go in, no one has any real sense that they understand what is actually happening on the ground. There is a lot of reactive work. There's a lot of hoping and praying and planning and putting stuff into the pipeline and hope it comes out the other end, right? So the reality is, most software environments, even though they might not be chaotic in the sense that you're not fighting a war or anything like that, they are actually fairly hard to reason about, right? And tools like Scrum, bring somewhat more structure into it by bringing sprints and iterations and inspect and adapt into the play. You actually create some enabling constraints. But I find that Scrum is not particularly effective at actually uncovering and solving the impediments because it lacks a theory, right? It lacks a whole idea of, okay, well, how should the system behave in the first place, right? And I think the idea of having enabling constraints, but then being able to say, here's how the system should behave, even though it's a complex system, helps you sort of be smarter about how you explore that domain, which is really part of how I do it, right? So I think you want to bring theory into it, you want to bring mathematics into it, and the mathematics will give you some parameters that you can play around with that then lets you sort of run experiments on your process and really sort of uncover the problems through inspect and adapt, but it's a much more structured process, right? And eventually, the goal is that you are less. So stability, for instance, is one of the goals. Stability is really about making sure that you end up much closer to this side, where eventually you can manage the system through process and constraints and guidelines, rather than be completely complex. But the world is uncertain. There's entropy in the system. You're always going to tip over into chaos and complexity at certain points in time. But you want to operate in a zone as a value stream where you can actually have some degree of stability, some degree of predictability, and know what those parameters are, right? So that's the goal of doing product development flows. The product development flow takes a system that's hard to reason about and makes it much easier to reason about, and gives you the framework to reason about it, which is built on sound theory, right? Questions, thoughts, comments? All right. tools play a big part in all of this, right? So our perception of the world is, unfortunately, for better or worse, through tools, right? Especially in larger enterprises, we don't see much about what is actually happening on the ground. These days, we don't even see people except through video and other things. So, our mediation of the world happens via. Everybody just disappeared. Am I still online?
Yeah, still on.
Okay, great. So the idea is that we have tools. We are able to look at the world through tools, but everybody sees the elephant from a different perspective, right? Engineers look at code. Sometimes they look at tickets. Your product managers, others are working on ticketing, on sort of road mapping tools. The customer support is working on Salesforce issues, and they all see the world from these different like entry points. And yet, all these tools nowadays are, have APIs. You can actually integrate them. You can normalize them, make a real actual data stream out of it. So the question is, what do you get when you analyze the flow of value all the way from any one of these customer endpoints all the way through production and back, right? So even including user tracking and so on and so forth, right? So building a system like this, what it lets you do is it lets you take a system, lets you take this system and actually sort of model it in such a way that you can actually collect data along all the layers of kind of how work transitions from a customer all the way to production and back, right? And that data is rich. There's a lot you can do with it, but it also, and so once you have the machinery to actually collect all this data, and in my case, we can do this in real time, which is that as things move through the system, we actually know everything that is happening about each individual work item, pull request, blah, blah, blah in the system, which gives you a huge treasure trove of data to start analyzing. And you're sort of almost overwhelmed. It's okay, what do I need to do out of this? So which comes back to the question of metrics. What metrics? I can give you 2 million metrics. Which ones do I pick, right? And so product development flow is a discipline that basically is kind of putting some structure to that, right? So what kinds of things do you look at? How do you look at them? What do you measure? How do you operationalize this on the ground, right? And so the goals that we use are varied. So we basically look at this pyramid of goals that you want to achieve. And it starts out with stability. Stability is basically letting the system work within capacity, which is one of the biggest sources of chaos in most software environments, because we don't know our capacity. It's hard to measure that capacity because it is knowledge work after all, right? On the other hand, when the system is not within capacity, it becomes highly unpredictable, right? So you cannot put something into a development pipeline and with any kind of confidence have a sense of when it'll actually get finished, if it'll actually get finished, and what the barriers are to getting it finished, right? So stability tries to move your system to the point where you can reason about it over sort of reasonable timeframes, and there's a technical definition for this, and measurable definition and a way to get there. So stability is the first goal. The second goal is quality. So your stability is typically only as good as the amount of entropy that's introduced into the system by random events, bugs, production defects. If you cannot control the amount of noise you have in your demand, which is directly a function of quality, makes it harder to sort of maintain stability. You can get stability, but you'll have a hard time maintaining stability if you cannot keep this under control, right? Once you have these two qualities in place, you can actually start reasoning about how do I allocate resources between value streams. You have competing value streams flowing through the same set of constrained resources in the system. How do you optimize the value streams across them, right? And this is really an art. I don't know that there's really a science to it right now, but part of this is providing data that helps people to understand, okay, this is underloaded. This area is underutilized. This area has more needs than others, and we can actually meet this need, and being able to sort of reason about this with some data that you can actually rely on, right? Alignment is something that's done completely by the gut today and almost entirely misaligned in terms of how things actually happen on the ground. So people think, for instance, that, you talk to a typical CTO, they'll say, well, my team is working about 60% on new features and 20% on defects. And actually, you go back and look on the ground, and they're probably spending like 5% on new features and probably 70% on defects, right? There's a complete mismatch because what people think is happening and what's happening on the ground are completely different, right? Value streams data on that sort of bubbled up from the bottom up give you sort of really, from a single source of truth, it gives you a really sort of good way to look at this even from an executive level, right? These are the things that you want on a day-to-day basis. And then once you do this, you are able to run at a sustainable pace for a reasonable amount of time, right? And once you get to that sustainable place, that's when you start thinking about resilience. Okay, how do I actually optimize for maybe getting better throughput out of things, how to reduce variability, how to increase efficiency, and so on and so forth. Most people focus on this first. I want to get more efficiency, or I want to get higher throughput. It's a fool's errand if you don't actually sort of build the foundation for doing that first, right? So we look at this as the foundation, and this is a nice to have. Often hard thing to convince people because they're like, I want my utilization to be up. No, that's not what you want. You want to actually be able to ship reliably first, right? And this is just, if you think about it, this is just a different lens to look at what things like, the Agile Fluency Framework, for instance, has been talking about for a long time. If you want to sort of roll out, make a team Agile, you have to sort of first get stability. Then you got to work on technical issues, quality, and so on and so forth. And then you can start working across teams, sort of getting alignment, being able to collaborate, and so on and so forth. And then optimization is always the last stage. So this is basically very much aligned with the way people have been talking about this for years. My main kind of wrinkle on this is I kind of bring some formality and data into the process, right? And to actually do all this well, you actually need a fairly big toolkit of things. You have to definitely understand queuing theory to some extent. Understanding alignment is really understanding graphs and relationships within value streams. The theory of constraints is your typical optimization. It's a brilliant bit of very simple, easy to understand theory. It's not even worth calling a theory, but it's a heuristic. But it's brilliant. It works, right? But it lets you think about utilization in a much more structured way once you understand where the constraints are, and that's what this stuff exposes, right? You also have to have a good idea of project management. Projects still exist today, even though everyone wants to do Agile, some things are better run as projects. You have to understand value stream management, obviously a good understanding of Agile methods and techniques, and not the least, modern software engineering. If you're still doing old school software engineering, all this is basically a pipe dream. You're not going to get there. So my diagram where I put a whole bunch of stuff as assembly line work assumes that's modern software engineering. You're doing stuff, you shouldn't have to manually deploy stuff. You shouldn't have to write tests, but you shouldn't have to manually test your software and so on and so forth. So this is basically the framework that you start with. Questions, comments? Am I running long here? Does this resonate?
Yeah, sounds good.
All right. Okay, so let's keep going, right? So what I'm going to do is kind of just as an example. So it's great to talk about this stuff in theory. Every one of these areas is fairly deep. There's an art and a science to, and I don't even claim that I understand it all. I'm figuring it out as I go along, really. But stability is something that I've spent a lot of time on. I understand this really well. I understand this really well. Getting somewhat better here, not so great over there. I think other people are much better than this here. So I'll talk about stability because there's some interesting ideas here, at least from my perspective, right? And again, like I said, the goal is to sort of bring data to the table, right? So use data in interesting ways and useful ways and ways you can reason about, as opposed to just showing metrics, right? All right, so stability is an interesting concept. So what is the idea of stability? As I said, it is the ability to sort of discover your capacity, right? So to be able to sort of work in such a way that you are sort of able to meet your commitments, but also understand what it takes to do that, right? In a way that you can reason about, right? And working within capacity is actually it solves actually one of the knotty problems that we always have, even in a framework like Scrum, right? Where you have this notion of this backlog that we know is supposed to be well groomed and so on and so forth, but there's a chicken and egg problem. We don't know how fast the engineers are going to ship stuff, so we either overstuff this or put too few things in it, and kind of maintaining a because the work of actually turning this tsunami of needs that's usually coming in into something that is a prioritized, refined backlog from product management. If you've done all this, you've done it, and I've done it enough times to know that it's a real nightmare of a job, right? So there's competing concerns. You don't know how long things take. Being able to understand how to sort of size this well-groomed backlog is a very concrete problem, and stability is a key to being able to do that. So what we really want to do is to be able to understand, what a stable delivery cadence is here, right? And the stable delivery cadence is not the same as the actual sprint, right? It is how far out can you sort of, even if you assume that not every sprint everything can get done in a sprint, what are the bounds you can place on it to be able to do that? That's a very concrete application to be able to say, I can confidently say that I have, let's say X days or 2 months or 3 months worth of work here that is stable. Maybe it's 2 weeks of work. I don't care what that number is. You can basically say there is a stable barrier here, which everyone agrees this is what we need to do. It's not too big that engineers will some of this will never get done. It's not too small that engineers won't run out of work, right? So that's one of the problems that we can actually frame as a stability problem, right? And solve it, right? And we'll talk about how we do that just in just a second, right? So, but it's the key to synchronizing it, because this is a highly variable, highly uncertain piece. This is somewhat more variable, but certainly not anywhere near as uncertain as this. If we build structure into the way we build code and ship code and ship changes to the system, we can definitely make this stable. Then we can use that to sort of understand how much is X number of things in the backlog worth in terms of actual wall clock time, right? And that's an example of synchronization between these two systems. If you're familiar with the drum buffer rope technique from theory of constraints, this is basically just a way of doing that, but in the software context where it's often hard to get the signal of when your thing is actually going down. It's a bit harder in this world when you're dealing with highly variable things that you're shipping, right? So the way this works is we lean on queuing theory, right? And a queue is a very general thing, right? Which basically tells you it's a process where something enters the queue when you start it and leaves the queue when you finish it, right? So it's a very general concept, right? All it depends on is the fact that things start and they finish, right? And you can build a queue around any set of events that start and finish, right? And queues have some very powerful properties that you can reason about. Certainly the work that is entering engineering is a queue by this definition, right? So stability has a very precise technical definition, right? So what it tells you is that if I look at a measurement window, let's call it 30 days, right? Maybe 60 days, whatever, call it whatever number you want, right? Over a finite measurement window, we can basically say that the rate at which work starts is the rate at which work finishes, right? All the work that is started also finishes. In other words, you don't actually have things that start and then never leave, which is a real problem in software, by the way. So it's one of the reasons why software is unstable, right? The number of items in progress does not increase or decrease unboundedly. So for instance, if you're familiar with Kanban, you know the idea of WIP limits. The WIP limits is a WIP limit, or a constant WIP, is an instance of this policy, right? So it doesn't really mean that you have to hold it constant. It just means that it cannot increase or decrease unboundedly, right? So you don't want this thing, starting and never leaving. So if you have things that never start and never leave, it often ends up with unbounded WIP over time, right? And this one is the most important. The average age of the work in progress does not increase or decrease unboundedly, right? And this one is actually a very subtle thing, right? So what it's telling you is that it doesn't matter if things are big and small. It doesn't matter if there's a mix of things that take 1 day versus things that take 14 days, right? What matters is that the average does not continue to increase and decrease, in an unbounded fashion, right? And this is actually the same set of principles that people use to run assembly lines, except that assembly lines are simpler, right? The generality of the system, right, is that a stable system behaves like a queue in the sense that you can think of work coming and leaving, even though they leave and arrive in different orders. They might be longer and shorter, but you can basically reason about them just like you can reason a first in, first out queue of things of the same size, right? There's no mathematical difference between them in the sort of size and shape of the queue of the things that go into the queue, right? And this works very well for software, right? So this is, as if you're familiar with it, what this means is that when a system is stable, it only starts as much work as it can finish within your observation window, right? So that means it's working within its capacity to finish what it starts, right? So this is great. I mean, this is simple measurements, right? We can measure this, and it basically tells you, it doesn't tell you what your capacity is, but it tells you, are you within capacity, which is good enough. It's good enough for us to start, right? There's a post in my Substack, if you want to look at it, that explains this in a lot more detail. I'll point to my Substack, but I've been writing this stuff in more detail, so you can take a look there if you're interested in understanding more about this, right? But the nice thing about this definition is that it gives you, a way to sort of discover the capacity of the system, right? So instead of measuring capacity, I basically start and stop work and figure out what it takes to finish everything within the period I started, right? I can play around with WIP, I can play around with sizes and so on and so forth. I can experiment with it, right? But it tells you very clearly, are you stable or not? And at any point, that you're stable, you can basically then say, okay, now I have a stable starting point. I can sort of figure out how to stick around the starting point. And that lets me start synchronizing with the business, right? And the stable cadence can be designed to the business. So let's say that the business wants stable cadence with stability over a 30-day window. That is your goal for designing stability, right? You work backwards and say, okay, I'm gonna work with, even though working on sprints, I'll work, with 2 consecutive sprints and make sure that nothing takes more than 30 days over 2 consecutive sprints. So that lets you sort of let some of these things, some of these errors go through the system, right? But you're actually observing the amount of work that starts, the amount of work that finishes, and so on and so forth. And with real-time measurement tools, the measurements are easy. These are all relatively simple measurements to do, right? So it gives you the tools to stabilize the system. And once you stabilize the system, then you can say, well, okay, I'm stable at 30 days. How do I do it? How do I become stable at 14 days? Okay, you might need to do some work to get there. Then how do I become stable at 7 days? You might need to do a lot more work to get there, right? And that's kind of the difference between, let's say, the mid-performing DORA metrics people and the high-performing DORA metrics people. People who can actually be stable at very short intervals, right? And the beauty is we don't really need to know the capacity to do this. We can actually discover this, through inspect and adapt as we go along, right? Questions, thoughts? And the beauty of stability is that, when a system is stable, these are the 2 most important things everyone cares about: throughput and cycle time, right? This is what you want: to get stuff fast. You want lots of stuff out the door. And Little's Law tells you that when a system is stable, that is, it satisfies those 4 conditions. There's an exact relationship between the average amount of WIP that's in the system, the average throughput, and the average cycle time. And this equation lets you do a lot of things, right? I can say, I want to be stable at a throughput of X and a cycle time of Y. What is my average WIP? I can ask that question and then work my way towards getting to that WIP. I can hold WIP at that level constant and see what happens. So this basically gives you the math to sort of play around with your process to understand where you need to be, right? So this is part of the sort of experimentation on your process to figure out. Or if you don't want to experiment on your process, you can measure the process as you do it, because we're using sprint goals and using goal-based, actually doing Scrum the way it's supposed to be. You should be finishing your goals within a sprint. That automatically means that you're stable. And if you're not stable, then you have to sort of figure out why, right? And you can use this as a mechanism to sort of investigate root causes, right? Because if it's not stable, it'll be one of the 4 conditions that are false. That's what this theorem tells you, right? And this is actually a theorem. It's a provable mathematical theorem. So it's not somebody's belief. It's not a maxim or anything like that. This is just straightforward mathematics. It'll always work. It's like physics, right? So we can use this to sort of understand stability, right? And if I want to make a system stable, you can look at each one of these metrics, each one of these conditions, and measure it. And you look at this, and every one of these is one of the standard maxims that you find, except maybe find and kill zombies. This is a very, very thing. Until you measure this, you won't understand what this means. But start, stop, starting, start, finishing is, everyone knows this by now. bound the number of items in the system, limit WIP, we know that. Very few people think about this, but this is actually the most important thing. Bound the average time system spend in the system, right? And since average age of work in progress is hard to do, typically the way you do this is actually put a time box around the overall age of any given item. So you basically say nothing that goes to the system will take more than X days, and you leave that as a constraint in your system, and you sort of try to hit it and play with what causes you not to be able to hit it, right? This one, the Walking Dead one, is actually interesting because this, if you're on an assembly line, this seems like it's a non-starter, right? I mean, yes, things that enter an assembly line are going to leave the assembly line, but not so in software, right? In software, we have infinite capacity to start stuff, provided we don't want to finish them, right? And we do, right? So there's things that are started and not finished all over the place when you actually sort of measure your system. And these create all sorts of chaos and noise. This is what makes a system unstable almost in every case. It's stuff that is started and abandoned with nobody knowing that it was abandoned. It's stuff that is not in a state where people think it's in production, but it's actually not in production. You find like all sorts of animals in this zoo when you actually look and measure. And this is one of the things that typically a flow analysis will uncover within a day or so, and it usually creates a lot of consternation because that tells you how much waste there is in the system, right? And this usually focuses minds, because once you get rid of this, you're basically giving a guarantee that we have a clear idea of what things are going to be in the system, and that if something is not finished, we'll know about it very quickly and we can take action on it, especially if you measure in real time, right? Thoughts, comments? Does it make sense?
Krishna, Andy has a question in the chat.
I'm not able to see. Let me stop my share for a second. I'm not able to see anything for some reason.
He asks, how do you account for work that falls into the following categories, and what to do if more of one category of work outweighs other categories of work, the categories being new features, bug fixes, and tech debt?
Yeah. So technically what we do is, obviously in order to collect the data for this, you have to have a fair amount of sort of understanding of the metadata in the system, right? But typically the way I model it is basically each of those is what we call a sub value stream, right? So features, defects, customer support, technical issues, security, all those are basically different kinds of workflows with different skill sets, different SLAs, and so on and so forth, right? So you can think of each of them as its own value stream with its own flow metrics. You have your backlog of tech debts, and the way you actually get rid of that backlog is different from your feature backlog. It's different from your customer support backlog, which is often more urgent. And really the alignment problem is exactly this. How do you balance all of this while you're working with the same thing, right? But at the level of individual items, if I want to stabilize it, if I'm moving 4 categories of things through the system, I want to be stable. Let's say I want to be stable at a 14-day window. The only constraint is no single item should take more than 14 days to get through that sprint. If I think it's going to take me longer, I break it up into 3 things and send it out. It gives you that discipline to actually slice work up into a meaningful set and actually get things through the pipeline. Did that answer the question?
Yeah, definitely. Thank you.
Yeah, and this is clearly it's one of the commonest problems. This is exactly what people want to, especially at the executive level. This is what they want to understand. They want to know how am I doing on all these different fronts, because all these things have these value streams have different flows, right? But they're actually going through the same resources. If they're independent, if I have one team doing bugs, then then it doesn't really matter. But the real interesting problem is there's the same team that has to do all of them, right? Because they are the only ones who know how to work this big piece of code here, right? And so sub-value streams and partitioning this by value streams is a technique that we use to sort of analyze them. And then that way you can keep track of your tech debt backlog and understand the flow and the size and so of that backlog completely separately from your feature backlog, because you're interacting with different groups of people on the other side of that equation in that defined phase over there.
Yeah, definitely makes sense. Thanks.
Yeah. All right. So so stability is basically, so when you look at, so this is an example. So for instance, I'll show you an example of Polaris, which is basically showing you, at a glance, what this kind of analysis can do for you, right?
You'll have to share your slides again.
Oh, I'm sorry. I'll share my screen again. I apologize. So this is an unstable system, right? So what this is doing is basically just checking for those conditions that we talked about in the back end based on underlying data. You can basically pick any subset of your sort of network and basically say, are we stable here? And what we're looking at is basically the relationship between work in progress, the throughput, the age of the things that are finishing, the age of the things that are not finished, that are still in progress, and what we call the motion of work. So essentially, motion. This is going to be an important concept we'll talk about in a second, right? Ultimately, the motion of things in a software pipeline is not guaranteed when human beings are involved, right? Unlike an assembly line, which we'll talk about in just a second, right? But the idea is that you build these flow charts and flow diagrams across subsystems, across teams. Even code changes to repositories can be analyzed the same way, right? Where you can basically understand how much work is pending that we need to work on, how fast is work moving, and where are the bottlenecks. And we can understand imbalances, at a glance, and then we can drill down into these things and look at it in a lot more detail and so on and so forth, right? But the idea is that we use this to build the focusing buffer. 3 months of supply is, in my book, it's not a focus buffer at all, right? If you want something that is stable, I want something like this. Very few items in WIP, almost everything is moving. Work in progress is, in the age of the work in progress is a lot smaller than the age of your cycle time. We are operating with a stability window of age limit of 7 days and a stability window of 30 days. So basically, typically, if I'm doing this, I probably should have moved this down to 14 days because it doesn't really matter. But basically, we are well within the window. So basically, things are getting through an average of 4.5 days, and that's high here based on what this is saying, right? Throughput is very good, very high. The age of the work in progress is less than the age here, right? And you can see that I have a very stable buffer of 21 days of supply, right? And at this rate, 21 days is an eternity, right? Because we have a lot of time to react. If I need to get work, I can basically move fast and get more work pulled in the system, right? So these are the kinds of tools you bring to the table, and you say, all right, you can basically plug this machinery in, understand how to use it, and then you can understand whether you're stable, and how to sort of fix stability problems. And obviously, there's more in the process over here, right? But as an example of how do you sort of use this data in a consistent fashion? So it's not just a bunch of independent metrics. You have to understand the relationship between these. You have to understand the relationship between age and motion and so on and so forth. There's a theory behind this that helps you sort of reason about the system. This dashboard as a whole is a holistic thing that tells you a lot about the system once you know how to read it, right? Questions, comments, thoughts?
Hey, Krishna, this is amazing. First of all, love your presentation.
Thank you.
In terms of this system, the Polaris system, what is your feed for this data? How do you get the data from? Where do you get the data
pretty
from?
much. So we collect data from a lot of different sources. So let me show you some examples. Let's see. These vary from customer to customer, but we basically have connectors to all the kind of standard tools like Jira, GitHub, GitLab, and so on and so forth. But we can also connect, a lot of stuff connects through Jira because many of these things have Jira integration. So we can tag stuff that comes from product board, which is road mapping tool. Road mapping tools push here. Salesforce gets tagged, but we can also connect directly to these to understand the workflow in that space before it gets to Jira, right? But the idea is that most of these tools have APIs, and we build connectors as needed. So we've got connectors to all the kind of standard tools people use. And we don't really sort of connect directly to Salesforce because Salesforce almost always goes into Jira, but product board doesn't work here. So this is PagerDuty, there's Jenkins. We're starting to play around with user experience and instrumentation. It's not really that strong yet, quite honestly, but the idea is to figure out how long it takes to actually get meaningful feedback from times, things get pegged to when they get used based on tagging. And then when those actually give you sort of actual actionable stuff as changes in your product roadmap pipeline, right? Very few people are sophisticated enough to do all this well. I happen to be lucky enough to have one client who's interested in doing this, so we're playing around with this. But It's experimental, I would say right now. So, but the goal is really, this is the holy grail, which is to do end to end, right?
End to
And
end.
like I said, I've been building this for a long time now. So I started about 6 years ago. So over the years, we've kind of connected a lot of stuff, and it's all pretty robust right now.
And going back to your dashboard, right?
Yeah.
When you're talking about cycle time and when you're talking about the supply and all that,
Yeah.
what's the unit of measurement? Because, it can be a feature, epic, initiative, whatever, right?
Absolutely.
Story.
Yeah, and it flow can be defined at every one of these granularities. So if I look at this guy here, right? So this is basically your hierarchy, right? So you can define flow for features, you can flow for epic sub features. It's basically a unit of work. And so when I do feature development, you can do it hierarchically. You can look at your portfolio itself and figure out how many of these major features are you actually slotting through the system, right? The principles of flow are the same, right? If you want to get a bunch of features, if you want to get a portfolio of features through the door, you should do them one at a time. You want to limit the whip. The same principles apply, right? So the idea is to prioritize the portfolio and get work in that portfolio done. Because when the portfolio features at the issue level are fragmented across the portfolio, your portfolio doesn't get done. It's simple, right? But you can do this. The interesting thing about this, once you apply these theories kind of relatively generically, you see that there's no difference between this diagram, right? Just like there's no difference between this dashboard. I mean, and that's the way we do it, right? There's no difference between this dashboard, if you're talking about features, pull requests, tickets, epics, it's all the same, right? It doesn't matter whether you're talking about tech debt, it doesn't matter whether you're talking about, so this structure is a flow structure. You can talk about the flow of anything, right? And so we train people on how to think about flow, and then your problem is, okay, well, your flow of features, what do you need to do? Well, the same things. Make sure your features get started and finished before, your windows are longer, obviously, for a feature in maybe 60 days. But if you want stable feature windows in 60 days, that's what you do, right? But the principles are the same.
Yeah, I get it. Thank you. And a follow-up question is regarding the breakup of the teams, right? If you're thinking in, say, for team topologies, there is the whole value, the stream-based teams, as well as the platform teams and things like that. I don't know whether you have any comments on that.
No, so one of the things that I'm very interested in team topologies. I think one of the things that this kind of machinery lets you do is it actually gives you ways to understand whether it actually improves the flow of work, right? Because the hypothesis is that having an enabling team should allow the team to actually either upskill something or offsource something that's not part of their core cognitive, reduce cognitive load in some dimension. So typically, if you have a good idea of flow and flow metrics for it, because we can do this for every team, right? So you can say, is this team impactful because they actually improved the flow of work in the other team? Or if this is a platform team or a specialized team, they are a constraint. So we want to manage the flow through that team very, 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 very carefully, because for them, that buffer is going to be hugely important, right? Because that buffer might include dependencies from multiple places and so on and so forth. So giving the ability to look at flow from that it becomes a question of how you interpret the meaning of that flow. For a platform team, typically you don't want the platform team to be a bottleneck, right? But if that platform team is embedded, with other people, what you want to see is the impact of that platform team in the flow metrics of the source team. I don't, quite honestly, it's still a theory in my mind. If I got the opportunity to work with somebody to test this out, I'd love to, but I've not actually sort of had the chance to actually test this with an actual team on the ground. So
yeah, last year we had
flow is everywhere, right? Everyone talks about flow, and this is the way you measure flow. So if your claim is that your process X improves flow, this is the way to measure it. Simple.
Yeah, Krishna, last year we had Manuel, who is the co-author of the team topologies.
Awesome. Yeah.
In this meetup, so we can definitely connect you. and see
Yeah,
if there is
I'd
any.
love to be able to. Yeah, I'd love to be able to test the theory because
Yeah.
according to my theory, it should be you should be able to test the hypothesis. You know, did the enabling team actually enable the team, right?
Yeah. Thank you.
Sure. All right. So how are we doing on time, Ron? You want me to stop talking? No.
All right, I have to unmute. We're doing fine.
Okay, cool. So one of the things, so I do want to get to the actual meat of the talk, which is our process and tools make it hard. But so when you try to go back here and figure out, okay, what does it take to do? What does it take to make a team stable, right? And this is what Agile coaches have been doing for generations, right? And it turns out a lot of the things that you're recommending on the ground are exactly the things everyone's been recommending forever. It's not that different, right? The main thing that this gives you is the ability to sort of very objectively and in a process agnostic way say, is it working, right? This is what you want to see working if you think about flow, right? So there are many ways to stability. This is completely process agnostic, right? So the only rules for stability are this. I mean, you have to limit WIP somehow, right? And you have to limit scope somehow so that nothing too big gets into whatever your window of stability you're trying to get done, right? And surprisingly enough, this is hard for a lot of people to do, right? And the tools have a lot to do with why, right? If you look at where we are, most real world systems are not stable. So one of the things that people always confuse stable with steady, right? Stable is not steady. Stable is basically just talking about, are you working within capacity or not, right? It's got nothing to do with kind of the size and shape of your outputs, right? So for instance, the example I used, I had a post again this last week on the Substack. The example I used there was, suppose you have a Scrum team that delivers a feature in an iteration, one well-chosen feature. And then the next feature, they work with customers to sort of refine it, fix bugs, get feedback, change quickly, and they keep repeating that, right? So in that example, over a 30-day period, that team is very stable, right? In terms of finishing the work they started, things not taking too long, getting to the goals, and so on and so forth. A well-functioning Scrum is probably the easiest way to get a stable system if you actually follow the rules, right? So if you think about setting a single sprint goal, achieving the things within the iteration, and actually sort of not thinking of Scrum, your iteration, as a bin packing exercise with a bunch of tickets like the way people do. Scrum done according to Scrum guide, is one of the easiest ways to get you to stability. You don't have to think about WIP and you don't have to think about any of the other stuff. The rules of Scrum kind of do it for you, right? But so few people actually manage to make it work for some reason. I don't know quite why, right? But if you are, so you can get stable using whatever process you want, right? The rules of Scrum actually sort of tend to have you bound WIP and scope automatically. But if you're operating on, something like a Kanban process, bug fixes, and so on, so work, which is more sort of ad hoc, repetitive, not driven thematically. If you do Kanban with WIP limits only, you might typically get, you've held WIP constant at, let's say 10 items at a time. One thing comes out, next thing comes out, and so on and so forth. You might actually be fairly consistent and steady with your throughput, right? But if you don't watch out for age, so Kanban without age limits is also not stable. So typically people say, well, if I do flow with Kanban, I have flow, right? I mean, technically that's not true. You have to actually also have age limits. Most, professional Kanban people actually do this. And so this is not a shade on Kanban anyway, but often people follow the sort of surface of Kanban, which is, okay, let's put some WIP limits and pull policies, and now we have Kanban. If you do that, you actually won't be stable if you let things run unbounded. And you have a lot of Kanban teams where nothing finishes. Things take too long, which is why a lot of product managers hate Kanban, right? Because they're not doing it right, right? Kanban can be a hugely effective product management, product development process too, if you just do these two things, WIP limits and age limits, right? So this is the foundation. This is the foundation. It is not a process or methodology driven thing. You can make this work with anything, any of these processes, from ad hoc process The rules are basically you want to have these two sort of constraints in place, and these are the key constraints that force you to sort of explore why you're not able to get to stability in the Kanban sense, right? Questions, thoughts? Okay, all right. So I said processes and tools make this hard. So this part is going to be somewhat less. I don't want to say deep, but it's a bit more facetious. So one of the things I always find when I actually go and figure out, okay, well, why the hell am I seeing this, right? Why the hell? How is it possible that this much stuff is like sitting, hasn't been touched in 200 days in the system? How is that possible? And the answer is usually the tools, right? So the tools and the way people use them are what cause, even the best laid plans to go awry. And, it's because humans are involved. We are error prone, we make lots of mistakes and nobody pays attention to stuff, right? And the root causes, if you look at the root causes of instability, as you said, unbounded aging is we can probably put WIP limits and make things, we can manage WIP relatively painlessly, right? But the aging of work is the hardest thing to manage, right? So, and aging can happen for a lot of things that we know happen every time, right? So multitasking, right, is a huge place. If somebody is working on 3 things at the same time, only one of them is actually going to move and the other 2 are going to age in place, right? And so this basically causes unbounded aging. Anytime there's a handoff, anytime somebody has to, hand off anything to anybody else, they almost always miss it. So again, one of those things is going to sit in age. Interrupted work. All of us get it. We start on working on something and somebody else wants to work on something else. The interruption means the interrupted work, loses focus. And then eventually, if you stay interrupted for a long time, everyone forgets that it's in the system and it stays around like a zombie, right? Lack of focus time. We know that as engineers, if I start working on something and somebody taps me on my shoulder, it takes another 20 minutes before I get back to thinking of what I was thinking on, right? Lack of focus leads to latency inside an issue. Or if I'm working on an issue, you'll typically see that things take a lot longer than they need to. I might have estimated a day of work, but add interruptions, add lack of focus time, in wall clock time, that ends up being 4 days. And we see this all the time, right? So the solution is basically, focus on keeping the work moving through the system. This is the thing that you have to do in software that's not true of any other kind of flow process, because the only way to sort of keep aging down is to actually keep the work moving, right? And so it's important to understand, what keeps work moving, right? I use this example of, and there's actually another post in the Flow Dispatch about this, right? One of the big differences between assembly line thinking, and software or cognitive work is, work, there is a conveyor belt on an assembly line, right? So work is just moving all the time, right? So there's no chance for this work to age in place because it's always moving and the person just works on it, or if you're like, Lucille Ball trying to keep up with the candies coming off the assembly line, you're the constraint. The work is always moving whether you're able to keep up with it or not, right? Software is different. Work is immobile by default. So until you pay attention to something, so if you think of Newton's laws of motion, the force that moves something is human attention, right? And without human attention, the work does not move. It's basically immobile by default, right? And so this is what causes aging, right? So this is the connection. Somebody asked me earlier about the connection between team topologies and the flow. Cognitive load is the connection, right? So the force of, in order to move something, you got to consume cognitive capacity. So you got to place cognitive load on the system, right? And so by examining the motion of work in the system, we can actually make some measurements that give you implicitly what the cognitive load in the system is. Either the cognitive load is focused in the wrong places, or it is overloaded and too many things are not moving, which is why this metric that I showed you here is actually a very interesting metric, much more interesting than you might think, right? This notion of what fraction of the work is moving can be used to make a lot of inferences about how much cognitive load is in the system, right? And this is kind of, we are still exploring how to actually really make this work in a way that's consumable by people. But this is a very, this is a key part of this. in software, this is a lot more interesting as a metric than our classic flow efficiency metric, which is based on sort of just states of active and wait states. The amount of in a stable system, you want to see high numbers of work that's moving or slowing in the sense that it was moving before, but it's starting to slow down, but eventually start moving again. So you'll see this flow of work in terms of motion, which is a very, very useful way of understanding why it's happening. And more importantly, since it can be done in real time, we can actually drill down into each individual thing, which is slowing or delayed, and figure out why it is not moving, right? So real-time action to keep work moving is what we actually need to do to actually make work flow through the system, right? And you have to do it. Somebody has got to push. Either your engineers are motivated enough to sort of focus on work on stuff, or your managers have to stay on top of them to keep work moving. But unless there's attention focused on every piece of work in the system, it will not move, right? And that's unfortunately what software is, So this is why we want almost everything here, right? The more people are involved, the more manual labors and attention are needed, and the more expensive it is to keep work moving, right? So this is the fundamental sort of thing that causes, and all the stuff we do are set up to not have work move. We have too many things in the system, right? So in the small, let's say understand how let's look at the venerable Kanban board, right? So Kanban board is great. A tool that all of us know and love, right? But it is set up in a world where it's assumed that motion happens by default, right? So there is no notion of aging, right? We are limiting WIP, limiting WIP by limiting the physical area on the board, right? It does not let you visualize aging of work. So I could look at this Kanban board and have something that was sitting there for 4 weeks, and no one would know that it's sitting there for 4 weeks because the Kanban board doesn't care, right? In a world where there's an assembly line underneath this, you'd be forced to move stuff because things are moving, right? And it's not motion aware. I cannot tell, what happened to this guy. You have to look at the Kanban board, and you got to go call somebody and talk to them. So this is one of the examples of, industrial metaphors that don't really sort of create flow on their own. They're useful. I'm not saying Kanban boards are bad. We have to have them, right? But you need things to augment them, right? To actually sort of understand motion, because motion is what keeps aging down, right? There's no other way to make aging down, and we don't have good tools. We've developed some tools to do that in Polaris, but I mean, and that's still pretty an early idea in terms of how people are sort of thinking about this in the mainstream, right? Electronic Kanban board is worse, right? So it doesn't even limit WIP using space. So you end up with things that can scroll off to infinity. And you have no idea how many things are in there. You have no idea how long they've been in there. Typically, the electronic Kanban board is almost information free when it comes to flow, right? Because it does not tell you anything that helps you do it. And so this is again why stuff stays. They don't move. Nobody knows why it hasn't moved unless you're a master, Scrum master who actually knows where everything is supposed to be. They don't see it, right? Hate to say it, but Kanban board is one of the things that makes stability hard in software development. But you have to augment it. It's basically what it is, right? So our tools discourage collaboration and encourage multitasking, right? So this is something I got from on the web. How to assign an issue to multiple assignees in Jira. So we tell people we want to collaborate on issues, right? And the answer is, you cannot assign one issue to multiple assignees. This is an impossible thing to do in Jira, right? Because this is against the principle of how Jira operates, right? Yeah, right. It does. I mean, because you don't want multiple people collaborating on stuff. But you can't assign multiple tickets to a single person. No, you can. You can have any one person have 10 tickets at a time, because multitasking is okay. And these are the two things that are exactly opposite of keeping work moving, right? This is again a artifact of where these things came from. They came from ticketing systems. Plus a little bit of industrial metaphor added to it. They're not designed for software, right? And I think if you understand the principles of how work moves in software, you will think of the world quite differently, right? Another big thing, if you're familiar with Tim Ottinger's article on scatter gather, this is I highly recommend it. It's a great post. It's something we always do, right? We parcel out work. Some godlike architect looks at all the engineers and says, yep, you're going to do this ticket. I'm going to give the back end to somebody's, front end to somebody else, this guy to something else. And all right, you all have your own queues, go work on them, right? And then the work goes into the system, right? If they all work parallel, that's fine, but you know that it doesn't happen. This guy has a defect, and so on and so forth. All this work, spreads out in time at different paces, and eventually, when it comes time to get together, there's no way to put them all together in one place. This is one of the most common work assignment patterns I've seen on engineering teams, everywhere I looked. And this basically all it does is add latency, right? What you really want to do is get all these people to sort of sync up on that one issue and figure out how they're going to connect together before they even break the work out, right? And if you can't do that, don't schedule the work, right? So this is Tim's got a great post on it. It's one of my favorite posts. And I always like get a chuckle when I read it. He's got a lot more detail on how this works.
I'm thinking Tim Ottinger probably was using this to evangelize mob programming.
Oh, absolutely. And I also agree. I mean, pair and mob programming are definitely a great way to keep work moving in the system and get great flow through the system. And even though and there's a way to measure utilization that actually sort of takes the utilization argument out of the picture completely for mob programming. From the standpoint of flow, it's actually better. So yeah, absolutely. This is definitely, but this is a real anti-pattern, because you see this. What happens is that if you look at an issue, I wish I had some couple of more things of how I visualize this stuff on Polaris, but you can actually look at an issue that essentially has three commits on it, and those 3 commits happen over 15 days. If those were actually compressed, that issue could have been done in half a day, right? So it's a very common thing. Essentially, the inflation of cycle time over effort, right? Which is purely a consequence of not being able to sort of work things in parallel together. And in the large, we have other things. Fragmented view of the system. Everybody sees different parts of the system, so work gets lost in handoffs. Especially across manual steps. We have processes that encourage industrial thinking. And so you basically have pipelines of tickets flowing down assembly lines, and none of the stuff actually moves. I've actually had I had an opportunity to sort of measure this for one small sub team of a safe team, and I could actually confirm a lot of this stuff. I'd love to see a whole safe team at some point and see what happens. My theory is that the flow would be pretty terrible, and it's good that they're talking about flow and safe right now, but my guess is they're going to have to change some of the things in other parts of safe to make flow work and safe. But again, I don't have proof of that, right? And the final result of all of this, you get this highly unstable system, right? And we can systematically go through and solve all of these things. I mean, I don't know that you guys necessarily. I have a couple more slides, but I don't think we necessarily want to talk through that. But the model is you don't have to be here, right? You don't have to be in this world. You don't even have to be in this world. Your sweet spot for software is somewhere here, where you can actually have some reasoning power, understand when things are unstable, know when they can get back, what you need to do to bring them back to stability, have high quality, lots of governing constraints in the system, and actually sense, analyze, and respond with using good practices to keep work moving through the system. It's very few people get here. Some people can stay here. Large majority of people are still here, unfortunately. That's my spiel.
Awesome. All right. Who else has whiplash?
Is there a question in the chat? Sorry. As I promised, out of left field, but it's hopefully it was an interesting talk. I mean, I'm maybe the first one to say a lot of this stuff is, I have a very small consultancy. I work with very few people at a time, so we're still building enough of a kind of base, and I spend quite a bit of my time building software too for supporting this project. So we're still building the machinery and sort of practice around this. And I'm very interested there's a bunch of people here who actually coach people. I'm very interested in working with coaches as well, to figure out how to sort of, I don't have as much of bandwidth to actually build that side of the practice. So totally interested in talking to folks over here. So
Yeah, any questions or comments? Just, feel free to open your mic and talk.
James was sharing a favorite tool.
Yeah,
Can we say
I've seen
about the
target. Yeah, it is good. Yeah, it is definitely good.
target process?
Yeah, target process is definitely good. Yeah.
One thing I would suggest to look at is introducing instability and chaos engineering. So stability has, a lot of cool things to value as far as an ambidextrous organization. But what I'm finding out is introducing instability creates innovation.
That's
Yeah.
that's an interesting observation. Yeah.
Yeah, and it's a balancing act, don't get me wrong. So where I work at a large pharmaceutical company, we are on the edge all the time with that, with especially scientific exploration and creating molecules. So even in our software engineering world, we introduce sometimes the ability for people to be creative. And that, of course, in the Kanban framework will push you to the chaos, but we also have the complexity domain as well as the complicated domain that we have to work on. Complicated domain and the simple domain is where you want to be stable, like in the lean framework. But what we're finding out is when we introduce these types of VUCA and chaos, we see more innovation,
Mhm.
which is very interesting because we're not trying to maximize flow or increase stability. We're trying to determine that balance, right? And of course, 90% of the time we get it wrong, but it's that struggle.
Right.
What do you think about that?
So there's a couple of points that you made. So one of the things that I try to sort of distinguish very clearly is stability as lean defines it and stability as is needed in software, right? So they're very different concepts, right? This is so even though they're mathematically the same, right? The parameters of stability, of general stability, are much bigger than what is typically needed in an industrial manufacturing setting, right? So a lot of these ideas here are a lot of lean stability is also coupled with steadiness, right? And the key point I always try to make is stable does not mean steady. So stable does not mean not innovative, right? A stable, if I'm running a highly innovative inspect and adapt discovery process using Scrum, that can be stable, right? And in fact, that is often stable by definition, right? Because of what Scrum lets you do, right? So stability, and there is certainly, you can be very stable here, right? But you don't have to be here to be stable. And this is one of the common misconceptions, right? People say that, oh yeah, you're trying to make this stable, so you're trying to make this look like an assembly line. That's not what we want. In fact, the whole point is you are trying to sort of build the same notion of stability and so on and so forth when the world is not an assembly line, when work moves separately and so on and so forth, right? So that's one of the key distinctions. This is to my mind a lot of the reason why people turn their mind off when they think about lean, because lean is very associated with this idea that we have building all the same things of the same type in a repetitive manufacturing. It's just a myth. It's just a misunderstanding of the process. Stability as a concept is exactly the opposite. So in an industrial manufacturing context, right, Little's law generally holds, right? It's almost stable by default, right? In software, Little's law does not hold by default, right? What you're trying to do is that's why I put the equation at the end, right? And the conditions in the beginning, right? So the conditions are what matter, because you're almost never stable, right? And what you're trying to figure out is how far away from stability are you? And the same law that can be used to maintain stability can keep you close to stability, which is the best you can often do, right? So the notion, unfortunately, maybe I should use a different term for stability, but that's what the technical term is, right? So we have to sort of lift our minds up and say, stability, looking for stability does not mean turning your domain to an assembly line. That is not, does not mean you can be stable here, right? You can be stable here, right? You may not be stable here likely, but you can definitely be stable in all these three zones. And what we want to figure out is how to be stable here, right? So that I think that is, so given that, right, then the notion of, getting instability, because of chaos will be just a matter of degree here. What does that mean? I mean, just let's say that, typically chaos engineering is kind of associated with entropy in the system, more than so stability and entropy are often in conflict with each other, right? So when you have high amounts of entropy, it becomes harder to be stable about the work that actually moving through the pipeline, right? So stability is a mechanism that's a counterweight. So if I'm actually sort of, you can be stable and innovative, for instance, there's no problem with that, right? But if you are introducing chaos engineering, if you're introducing stability in the system, the notion of resilience is the next, the top of the pyramid is what lets you sort of figure out how do you actually react to that introduction of entropy into your system, right? And that's from a queuing theory perspective, that is handled by the notion of utilization and variability, right? So you have to understand, if you're highly utilized, then you're not resilient, you're not able to react to chaos. So if you want same principle of how you run your servers, right? If your database is running at 90% utilization, then it topples over, right? The same principle at the moment chaos happens. The same thing applies to any queuing system, and software development is a queuing system, right? So the tools are there to talk about it, right? I can't say I've actually sort of, again, at some point I'd love to be able to sort of see some data and actually confirm these theories, but the framework to think about it is there. How do you actually deal with introduction of entropy into the system, and what parameters do you need in the system to maintain stability even in the face of entropy, right?
Yeah, and what we're finding out is that sometimes you can manufacture entropy, and you can determine whether the value produced and the outcome produced is significant or insignificant.
Can you give an example of how this a concrete example of how it leads to innovation, like for instance?
So let's so in organic chemistry and 3D molecular design, we can create a situation with technology today to where we can create models to determine the molecules and proteins over thousands and thousands of reputations to see if these significant characteristics will happen. So if we investigate diabetes 2 or Alzheimer's, we can introduce a lot of these experiments to see what will happen, different than what's in a lab. These are digital references by which we can do this, which is not normally done in organic chemistry. Okay, it's a different way of using technology to do this, just like Gen AI, right? And what this does is this introduces changes into the cognitive reality of humans and mindsets of what they're used to doing, right? And it's humans react to this, right? To say, oh my goodness, this is introducing chaos and entropy to our norm, right? How can we adjust to this and use it to determine diseases or solutions to diseases like Alzheimer's, right? So that's what we're doing today, right? And this is introducing chaos into the normal way of how organic chemistry is done.
Mhm.
Okay, which then changes the human perspective and the paradigm, right? So that's an example of how these things can happen with intent.
Yeah.
Does that make sense?
Yeah, it makes
Yeah,
sense. Yeah,
what I've seen is that a lot of companies want to have predictability, so they get
Yeah.
into a very much of a incremental improvement mindset, right?
Yes.
But when you want to innovate, you need to have people look at things from a completely different viewpoint, right? No, every innovation comes by looking at things differently than you did before.
Mhm.
So you have to get out of the mindset of we're going to do everything we did before with a little bit of improvement. You have to have the freedom to tell people we're going to do things completely different this time, and then we're going to do things completely different this time, and do things completely different this time, right? And it's a very different approach. You know, when I hear the word optimization, I always cringe. I hate that word because that's like telling people don't do anything that's too good. Just do something a little bit better than before, right? You want to tell people break things, you know, make a mess, go out there and try something completely different. And then that's when retrospectives become really quite engaging, because now you're going to say, what did we learn from that? Right? What do we find? What can we use? And those are the kinds of, and I always tell my teams, when you have your reviews with your stakeholders, you want to tell them the bad news as loud as the good news. And the other thing you want to tell them is, what did we learn? Right? Because you can take the seeds from your discovery and you can spread them out across the whole company.
Yep.
So that other people can learn from each other, and then the innovation goes a lot faster, as opposed to just let's do things a little bit better.
And I think the challenge is that, you know, there's all sorts of companies with all sorts of needs, right? So I think there are several companies where the optimization is the thing to do. I mean, there is the problem to solve, right? And so you have to pick your battles. So I think that you know, a lot of the people I work with are growth stage software companies.
Yeah, I'll give you a really good example. I just wrote a book where I did a lot of research on this. And Nokia back in the early 2000s, right? They had 35% market share. They were huge, and they optimized themselves to death. Literally, they died because nobody was worried about innovating new things. So even if you are the market leader, and even if you have huge share, they're making 4 billion euros a year in profit, but nobody thought about doing things differently.
No, yeah, I mean, this is a well-known story, right? So it's part of it's a tool. You got to use it when it's useful. If not, it's not useful, then you don't do it, right? It's also, I think, you know, just as silly to say, well, I don't care about optimization because it's not important. There are many places where it is important. So you know, it's not an either or, right? So I think that there's no absolutes in most of these things. I mean, there are lots of very useful use cases where people really need to optimize because that is a task at hand, like, you know. So and when you do, these are the tools you bring to the table. That's all it is, right? So
yeah, well, I think flow optimization, I think optimization is important to keep a company going. Okay,
yeah, absolutely.
You're going to be profitable or not, right? If you're not, you're going to die, right?
Yeah, and if that's all you do, then you'll die too. So
exactly.
That's my point.
Yeah.
Yeah. At the same time, you got to innovate. If you don't innovate, you don't change the world. Right. And,
you know, I think you know, the way I look at it, Jarvis, is like, I'm a pretty pragmatic person. I think what I look at is like, you know, yes, innovation is sexy. Everyone wants to innovate, right? But sometimes you gotta just do all the shit work that need to get done, because when you don't, you know, and this is at least a systematic, rigorous way of doing it, right? As opposed to some ad hoc, you know, if you're trying to optimize, you might as well do it right. So that's the philosophy. Yeah. So.
Yeah, I agree.
So I want to ask a question. Yeah. So going back to the Cynefin, and I'm going to tie it back to Jay and James, what you were saying. Back to that Cynefin drawing, and your thoughts on Cynefin, Krishna. I would agree that I would totally agree that there are too many software development shops that are ad hoc. And I would absolutely equate ad hoc and chaos. I think that's a good equate. What I'm questioning though is the no estimates people, not my favorite people, not my favorite term, because they actually don't mean no estimates most of the time. But the no estimates people and the Monte Carlo people, I think, will both tell you that product development is by definition complex, that you cannot move if it's innovative, if it's not optimization, if it's innovative, you cannot move it from complex into complicated. I have to disagree with them, but
Yeah.
and James and Jay, one of my favorite phrasings to teams is, what experiment can we try?
Right.
And experiments are, I think experiments can be stable.
Experiments can be stable, and I think the point. So I think so I'll be quite honest with you. I think Knevin in many ways is very confusing to me. I think I think I understand what Snowden's saying, but I may be wrong as well in terms of how I'm interpreting it. But the way I look at it is there's a distinction between the domain that you're exploring and the process that you're using to make that exploration, right? And what I'm focused on is the process that you use to make the exploration, right? And to me, that process, if you are trying to explore a complicated domain with a chaotic process, that's not going to work, right? Your process has to be simpler than one level simpler than the domain you're trying to explore, right? So
Not that it's not going to work. It's just random.
It's just random, right? So I think the difference between and like I said, I don't claim to understand Knevin that deeply. And so I may be saying something that's factually wrong here, but I think that to me, that's the way I make the difference. I'm talking about experiments on the process. I'm talking about experiments on, not the experiments on the domain to figure out what your solution is. I'm talking about experiments on how you improve your process, right? By figuring out how you can collaborate better, right? And I think if you're a 5-person team or a 10-person startup, none of this stuff is needed, right? This stuff happens at the scales of 50 engineers, 200 engineers, and so on and so forth, where the organization itself is trying to get something big done, right? And you're trying to get the complexity of the system is because you can't sort of understand the sum of the parts. They behave in very strange ways, right? And so you're trying to sort of bring some structure and stability into that complex space, right?
Yeah, so complexity science and Dave Snowden and I, so it's an emergent thing, but once you get involved into the system, you change the system.
Yeah.
The system evolves, right? And the domains are very, very different in how you react to the domain and the practices and activities you can do to solve the domain. And you can go back and forth between domains, right? So that's something we're exploring, and Dave came out with estuarine mapping now, which can help with those clarifications. But it is very important, because when you talk about stability and everything, you're talking about the complicated and simple. You can't have stability in the complex domain. It does not exist. Okay. So in complexity science, there's no stability in complexity, right? Because there's too many unknowns and too many variables, right? So you cannot have stability there. So what most companies and organizations and people do is they try to bring the complexity domain into the complicated and the simple domain so you can have stability, okay? So that's the difference, okay? So if you're working in the complex domain where you have a lot of variables and a lot of unknowns, where you have to probe and respond and everything, there is no stability. That's the whole point. The whole point is you're trying to create stability.
Data science, for example.
Exactly. So and every company has pieces and parts of their company and organization and process where they're going back and forth in all these domains, right? And they focus on certain things. So lean is cool for manufacturing. That's a simple domain. You want to keep doing the same thing over. The complicated domain is where most software engineering happens, right? It's very complicated. You have, specialization and excellence and practices, best practices or leading practices, right? But once you move into the complex domain, then the world changes, right?
Right.
So just keep that in mind.
But it's, the one question I have on this is like, what makes, so give me an example of a 50 person software company building a product. What makes their engineering process inherently complex? What can you give me? Sort of, can you break that down?
Yeah,
for me?
sure.
Yeah.
So when I first worked with Watson and IBM, I worked for IBM for 20 years.
Yeah.
When we first developed Watson and AI, it was a complex domain. We call it an IBM first of a kind. It's never been done before, ever. We had to create something out of nothing, right? And we did this.
This is the process of creating Watson.
Yes.
Okay.
So
Or is it the solution to Watson? So Krishna's trying to differentiate process and solution.
yeah.
And
So-
Watson's definitely a complex solution.
Solution.
Correct.
Right.
At the beginning it was. Now Gen AI, everyone does it, right? But at the very beginning, nobody
Started.
ever done it before, right?
But was the process you used to create Watson complex?
Scientific process is a scientific method.
That's just complicated.
No, it was complex in the sense that there was a notion that we could create something that never existed before. And if we and no one knew how to do it. And we had to bring certain people together to figure out.
Well, that's fair. I mean, that's
how to do
innovation.
it.
Innovation is inherently.
Yeah,
you
Right,
don't-
but if you break that thing that we don't know how to do into what's the simplest experiment we could try that might tell us something?
Right.
Yes.
Then
I think that
process
drives
is
it into the complicated.
Right.
well,
Then-
yes, eventually it does get there, because if you
Not
probe,
eventually, right up front.
Right away.
What's the first thing we can try? What's the first experiment? Because the experiments are complicated. The whole thing is complex.
correct, that is correct. So
I think
It's like
that's the
data science,
distinction,
we don't know whether we're going to get a result, right?
exactly,
Right, so
exactly.
it's an experiment, and we may do the experiment over and over and over again, just retrain our model.
That's correct, but I will go further. So a more complex domain is something that is very difficult to solve, like universal hunger, or the COVID-19 problem in the governments, and how the world is going to react to COVID-19. That's a complex domain where you cannot control or even envision how the world is going to react and all the governments are going to react. Right? So one government says, okay, in China, we're going to do this. And then all of a sudden America does this and London does this, but you don't know how that is going to interact with the organic parts of the world and all the people of the world. It emerges and you have no control over the emergence. None. It just happens. And then you have to react to it and then adjust. That's a complex domain. So we just went through it with COVID-19. No one knew what the frick was going to happen, and everyone tried to do certain things and stuff, and then all of a sudden you saw interactions and reactions across the network of the world and the human beings in the world. And no one could have anticipated that, planned for it, or even envisioned what could have happened. That's the complex domain.
Right.
So
And I think-
Doug's
yeah, and I think-
applying
I
it to
think-
software in the chat and saying, isn't 150 people coming together to work on a new solution enter into the complex domain? I think so. My answer is yes. That's a complex problem, much
Mhm.
as. But what's the smallest experiment we can try?
Yes.
Might lead us to that might show us whether we're on track to that solution or not. And I don't think that is complex.
No, then you move to the complicated domain.
Yeah.
Yeah, exactly. But
Yeah, and this is
at one
this is
point in
part of the
time,
reason
you
why-
were in the complex domain until you could figure out how to move to complicated domain. You follow me?
Yeah. So Doug, you turned on your video. Go ahead.
I mean, I'm just thinking about one of the companies I work with, and and just getting human beings to work together on knowledge work is so complex. And you run into things that you wouldn't even think that you run into, because no one even talked about, organizational structure and existing systems and middle management that are trying to protect their bonuses and all this other complexity, and trying to figure out, how to solve those problems as well.
I think you need Krishna's help.
Yeah, no,
Yeah,
so
yeah.
I think
I even need Jay's help. I like I guess somehow in Jay's organization they bypassed all that stuff.
I think the point, Doug, that you just made is like the thing that I think I have not cut across in what I've talked about in calling the stability, is that the goal here is to figure out a stable operating point for a certain amount of time. You're not going to. So the idea is, when you say keep work, so the principle is keep work moving, right? And that is what you mean by making people collaborate, right? And this is a constant struggle. You're never going to get into one point and stay, keep work. So the goal is, in order to get people to collaborate in software development, you have to keep work moving, right? And when you do that, you have things that look like stability. Work is moving smoothly. Things are moving through the stack. You may not stay in the same place. You may not be at the same cycle time or throughput forever. It's not steady, right? But the invariant is you are keeping work moving. And that is what we call flow in collaborative knowledge work, right? So I think the definition, so the way you define flow is very important, right? This is why I say the assembly line, the conveyor belt doesn't exist. I think this is what's hard about the human beings, right? They don't collaborate, they don't cooperate with each other, right? So you have to. So mob programming is a great example. Mob programming is a operational way to keep work moving by getting people to collaborate on the same thing simultaneously, right? But this is the general principle of how you do that in software. So in other words, in an assembly line, limiting WIP is enough, because the assembly line takes care of the motion, right? In software, you cannot. That's not enough. You can limit WIP to 1, and nobody's paying attention to that one item. It's still sitting there, right? So the idea is that you have to apply the principles of queuing theory to understand where to operate, but the force that you have to do, the measurement. The point is that this is measurable, right? So the idea of are people collaborating to keep work moving is actually measurable, right? And so in a software context, that's hugely important, because that's where things fall through the cracks, right? There is things that are in the pipeline that no one knows are in the pipeline. This is the cognitive load issue, right? So when we look at, this is why I say, when I look at flow in software, the questions you ask are not, do you have the fastest cycle time or the lowest throughput? What you're looking for is, are you sort of keeping work moving through the system, right? So that things don't sit around forever, right? And that is true whether you're doing innovation, whether you're doing, whether you're doing any kind of work. If the things that you have in action are not in motion, right? As a software manager, engineering manager, that's what you care about. In the end, of course, you also absolutely care about the outcome, right? But if things are not moving, then you're also not thinking about the right things in the right place, right? So I think that the point I'm trying to make here is, the ideas of flow are very important, but the way you operationalize flow in software is very different from the way you do it when you have motion by default, right?
I'm curious, how do you sell this flow concept to an organization that wants to organize around their component architecture? And so you see a lot more handoffs between teams.
So I think the way you do that is you're able to actually visualize the cost of those handoffs, right? And you can actually manage kind of how to sort of minimize the delays around those handoffs. I mean, you will typically, most of the time when you look at this, we look at the costs of whatever structure they have, right? So if I have a lot of handoffs, then you don't have flow, right? So if you're comfortable with flow, if you're not having flow, then that's what you get. The time it takes you to ship is going to be infinitely higher, right, than if you actually didn't have those handoff barriers, right? And maybe you don't care about that. In that case, you shouldn't care about flow. I mean, that's all it is. It's not it's like I said, my sweet spot market is growth stage companies that care about getting things to market. and then don't have the are having trouble getting there, right? So I think time to market is an important
Right.
important driver. So yeah, if you don't need it, if you don't, it doesn't move the needle on your business. Yeah, don't do it, right? So
Yeah, one of the pieces to that, Doug, is so help me out. Inventory and process, inventory stock.
work in process, yeah.
Rigor process. Yeah.
Well, work in process is generally used as a number, but we want to limit the work in progress. But when Bob, who's working on the back end, gets done, and the front end and the database work aren't done, then that becomes inventory.
Yeah.
And it's inventory that's stuck. And not only is it stuck, but so we're talking about cognitive load. There's that context switching. So Bob by management is told, well, you have to be busy, so you have to go work on something else. So Bob starts working on something else, and now he's got a context switch to one, remember the file that was in, remember the files that he was working on when Sue and Sally get done with the database and the front end work, and come back to it and probably put that other thing that he was working on in as inventory, becomes inventory, because he's not working on that. And I think there are some mechanisms for demonstrating that. I remember probably 15 years ago, Chris Sims did if our team works on two things and they each take a week, but we start on both of them at the same time, so we're multitasking. When's the earliest thing gets done? Well, the earliest thing doesn't get done for 2 weeks. And if we can assign revenue of $100,000 to each of those things, then we can capture $100,000 by working on only one of those things, and then working on the other one. And I remember the first time he showed that to me, it was like, oh, really?
Yeah.
Oh, that's really helpful.
That's latency and cost of delay, right? So those are the two things that basically factor into that. So latency is what happens almost everywhere, right? You have dead work, half finished work, unintegrated work, and if you actually look at it as you can actually, interestingly enough, when you have the data from Git and so on and so forth, you can actually measure the cost of that unmerged code sitting on branches, which often will not be mergeable when you get back to it, right? So I think you can actually even associate costs with that, right? For people who are interested in figuring out how to cut this stuff down, these arguments are actually relatively useful, right? And they actually encourage good practices by appealing to things that that we might not necessarily as engineers be as thinking about, but a lot of these things, a lot of the benefits of flow are very well aligned with the things that we actually should have people do anyway, as a matter of good technical practice. But if you tell them do it for good technical reasons, no one listens. But if you tell them, yeah, I'll actually improve your flow and show you, they'll actually do it. So to me, that is one of the reasons why I find this valuable, because it's a language that business lets business do the right thing.
Like having Bob and Sue and Sally mob program, instead of working in silos. And the first one done is then said, no, now you got to work on something else.
Yeah.
I am curious though about how to actually get because the biggest thing is having the data to prove what what you see is actually what is happening.
Yeah, no, and it's a very good question. So it's a matter of actually, because we have, so in the case of my practice, it's a real-time system. So you can actually run this, while you're working if you want to, right? And see the numbers show up right next to you if you want to. So if you actually want to see, why does this thing why does it say that the cycle time of this story is 4.3 days? You can actually see that, before you start the story and finish at the end of the story. Although I don't actually use it that way, there is enough granular detail for people to check. They check that the numbers are backed by things that they can actually see. They can go back and trace a story or look at a ticket. And people actually use it for sort of doing retrospectives. So understand, okay, why did this take so long? You can look at that and say, okay, well, this takes so long because X, Y, and Z happened. And the person in the room say, oh yeah, that did actually happen. So it is backed by very granular data, but that is just an artifact of the way I have done things. But often people have metrics and they just believe the metrics or they don't believe the metrics. That's it. I don't know. It's it runs the gamut. There are a lot of people who are very skeptical, who actually want to kick the tires and see everything. A lot of people look at this, oh yeah, that makes sense. I see this, and so this data is showing me that, and that's fine too.
Yeah, so one of the things that we're doing right now, we're doing the flow and the cycle time and dynamics and on those output metrics.
Yeah.
We're tying it to the actual OKRs and the outcome and value metrics. So the leaders, the executives really don't give a shit about the output metrics or the flow or any of that stuff. They want to know, are we delivering the value and the outcome that we desire, or the goals that we're trying to measure for the company, right?
That's the right way to do this. Yeah, this stuff should not be, typically I always say if your CEO is looking at flow metrics, it's wrong, right? Because they shouldn't be looking at the flow metrics, right? But the CEO cares about the change in the process that lets them see whatever result they want, and that's ultimately what matters. So yeah, these are the same with Dora metrics. You shouldn't be using Dora metrics in the boardroom. I mean, that's it's simple. You don't, right? These are operational, engineers and product managers and developers kind of trying to figure out, how to make sense of what they're doing, right? And ideally, that's the level at which I like people to use it. I'm not always successful because there's a lot of resistance to this kind of stuff. Just that's our industry. There is a lot of resistance to this stuff. So when people are enlightened and understand the reasons for it, it works. A lot of the time it doesn't work. So it's
well, with that great epiphany, I'm going to end it. It's 10:55. And I want to thank Krishna and Kumar, and wonderful. It was fantastic. A lot of learning, a lot of evoking thought. And Ron, thank you very much for bringing this gentleman to our group. This is going to be recorded, and I'm having problems with YouTube. I'm fixing it, and I'm going to upload it. But thank you, and thank you everyone for participating.
thank you, everybody.
All right. Bye.
Thank you, everyone.